Hello, class. Today we are going to continue on through Chapter 9. We're definitely in the home stretch. We're going to spend a few days on Lesson 9.3 and a few days on 9.4, and then we'll be all done. So great job with e-learning. You guys are doing a wonderful work, turning good things in on time. So keep up the good work, and let's hit the home stretch here. So lesson 9.3 talks about complex numbers and the complex plane. So you were introduced to complex numbers last year. You might remember something like the square root of -1 equals I, and we would call that an imaginary number, or oftentimes a complex number, because it's not a real number. And I do want to kind of clear that up a little bit as we get started here. So complex numbers actually include real numbers and imaginary numbers. And so complex numbers are those that take the form z equals x plus yi. Some textbooks or sources might use a and b instead of x and y, but our textbook uses x and y, so I'm going to go with that. And so x is the real number part, and y is the imaginary part. And so you'll see how the y here has an I attached to it. And so just to kind of clarify how complex numbers could be real or imaginary, it all has to do with the value of y. So if the value of y is 0, then you don't have the yi term and you just have x, and so you just have a real number. If y is some other number besides 0, then you will have an imaginary part. Thus, we would call the complex number an imaginary number. So complex numbers really make up all of the numbers we've ever studied in math class. Some of those numbers are what we would call real, and others are what we would call imaginary. And then from there, you have subsets like real numbers. We have rational and irrational. And then of the rational numbers, we have integers and whole numbers and natural numbers. You might remember those conversations from classes in the past. But complex numbers include all of those, real and imaginary alike. The first thing we're going to do is look at what we call the complex plane. And your first thought will probably be that the complex plane looks a lot like the XY coordinate plane. The only difference is, instead of calling the x-axis the x-axis, we call it the real axis. And the y-axis, what we would normally call the y-axis, is now the imaginary axis. And so if I have a number like 0.8 here, that would be something like 2 plus 3i. So x would be 2 and y would be 3. And so you would go over on the 2 units over on the real axis, and then up 3 units on the imaginary axis. And that's where the point A would be located. For the point D, it would be something like -2 plus I. So you would go left 2 on the real axis and up 1. There's a coefficient of 1 hiding there. You would go up 1 on the imaginary axis, and that would be where point D is. And so that's how the complex plane works. The x value, or the real value, is the direction you go left to right, and then the coefficient in front of I is the imaginary part, and it tells you how far to go up or down. So the rectangular form of complex numbers is z equals x plus yi. That's what we saw on the first slide. So now, to kind of merge two thoughts together, is let's take this idea of complex numbers, and what if we wanted to write them in complex form, or sorry, in polar form. Okay, so we're kind of merging the idea of polar coordinates and polar form that we studied in lessons 9.1 and 9.2. And so we can do that real quick. Let me show you the transformation. You might remember from earlier lessons that x equals r cosine theta, and that y equals r sine theta. And so if we want to change this rectangular form into polar form, we can do that by first making those substitutions. And so we'll start with x plus yi, but we're going to replace x with r cosine theta. And then we'll replace y with r sine theta. So that leaves us with r cosine theta plus r sine theta I. So the I, the imaginary part, is still there. So then we can factor out the r. And so now we have r times cosine theta plus I sine theta. And so this is our polar form. However, you're going to notice that we're going to use this polar form a lot. And so what I'm about to do next, our textbook does not show this, but this is a pretty common kind of a shorthand notation for polar form of complex numbers, and many resources use it, and it's something that I'm going to refer to throughout the next several lessons. And so these two here are identical. These mean the same thing. This is just a kind of a shorthand version of this. And so you can see like the C comes from the cosine, the I comes from the imaginary part I, and then the S comes from the sine. And so the way I would say this would be Z equals R cis theta. And so if you're comfortable with it, I would recommend you using it. It's a lot faster, a lot shorter, just a kind of a shorthand notation. If you want to write out the whole thing when you're writing a number in polar form, you're certainly welcome to. But from this point forward, I'm going to use this cis notation almost exclusively. Okay, so in your homework today, there's 3 types of problems. I'm going to run you through 2 examples of each type. So the first type, what they're going to do is give you a complex number in rectangular form and ask you to convert it into polar form. And notice it says express the argument in degrees. I know the book or myself usually leans towards radians, but they're asking us to do degrees. So if faced with the choice, I guess we'll do that. And so this is our x value, and this is our y value. I think actually I'm in these directions. If I remember correctly, the book asks you to first sketch a graph, just a little a sketch, if you will, of this. So if I were doing that, I would just make what we would formerly call the x and y axis, but now this is our real axis. I'm going to put an R for real, and then this would be our imaginary axis. So I'll put a lowercase I for imaginary. And so if I were plotting this this point, I would go over 4 units along the real axis, and then since it's negative, I would go down 4 units for the imaginary axis. And I know that I'm going 5, but I just like to put a little space after the fact. And so if I go over 4 and down 4, that's going to put me right about here. And then maybe I'll just kind of, this is where my angle would be. This could be helpful to me here in just a minute. In fact, I'm going to go ahead and draw my triangle and think about my reference angle, because that's going to help us out here with the second part of this. And so here's our coordinate, 4 minus 4i. And so your first few homework problems are going to ask you to draw a sketch of that coordinate. And then they want us to put it in polar form. And so if we go back to our polar form, we need r and we need theta. So if we can find those 2 things, we're in business. And so we're going to find r the same way we did before when we changed real numbers into polar coordinates. So we'll just use the Pythagorean theorem. So we know this is 4 units. We know this is negative 4 units. And so using the Pythagorean theorem, I'm just going to say r equals the square root of 4 squared plus negative 4 squared. So doing just a little bit of math, we get 16 plus 16. So that's going to be root 32. And if we can simplify that, we certainly like to. And what I mean by simplify is not to just round to some decimal, but instead to pull a number out if you can. So 32 is 16 times 2, and the square root of 16 is 4, so we could call this 4 root 2. Okay, so we do like to give exact answers, so I think if possible, and so I'm just going to leave that as 4 root 2. Okay, and then we also want to find theta. So theta is going to be the angle that we rotate from the polar axis to get to this angle here. And so just as before, we're going to find theta the same way. Sometimes it'll be obvious what theta is just by looking at these values, just from our knowledge of the unit circle. And if not, we'll use tangent to help us out. So in this case, since both x and y are roughly the same, I guess one's positive and one's negative, but since they have the same absolute value, that tells me that this reference angle in here is 45 degrees, or I suppose negative 45 degrees, since we're going backwards, if we were to go this way. And so since that angle is 45 degrees, that means if I were going forward, it would be 45 less than 360, so that would be 315 degrees. Okay, so sometimes we can kind of use our knowledge of the unit circle just to know or guess, maybe not guess, but to know that that value is 315 degrees, and so that's our theta. Again, if you can't tell, if those ratios aren't common enough to you to know what that angle is, we can always use inverse tangent as our backup. I think we'll probably do that on the next example. All right, so we really have everything we need. If we go back again, we're just looking for r and theta. So if we have that, I'm going to use that cis notation that I just referred to. So my coordinate is going to be r cis theta. So if I wanted to say, I could say z equals 4 root 2 and cis 315 degrees. And that's our answer. This is our polar form of this complex number. You don't have to do anything further. That's it. If you wanted to express your answer using this notation, you would just say 4 root 2 times the quantity cosine 315 plus I sine 315. That's what this cis notation means. But again, I think we'll prefer that shorthand, and I'm going to use that notation moving forward. All right, here's one more, same directions. Again, we might just draw a little sketch here. And, you know, the sketch can be helpful as far as answering the question too. I think having that reference triangle can kind of help us think about whether we know the value of theta or not without having to use the inverse tangent button. So I think it's useful, and I'm going to go ahead and do it again. So -2 is my real, so this is my real axis. So -2 is going to be over here, and then along my imaginary axis, I'm going to go up root 6, and so root 6 is greater than 2 but less than 3, a little bit closer to 2, and so that's going to put me somewhere right in here. And so then I'm just going to show that angle. I think I'm going to use a dotted line about this one. Okay, and so again, we just want to know the r value and this angle here. So for the r value, I'll just use the Pythagorean theorem again. So keep in mind, if I complete this triangle here, we know that this is 2 units or -2 units, and this one is root 6. And so I'm going to go -2 squared plus root 6 squared. And so that gives me 4 plus 6, so root 10 is going to be my r value. And then to find the angle, again, we can use our knowledge of the unit circle. Or if you look at this, I see a 2, a root 6. This is root 10 over here. I don't know what that angle is. And so anytime that happens, that's no big deal because we have a good backup plan. We know the tangent of that angle, you might remember doing this a few lessons ago, is y over x. So that's going to be, actually, I'm going to rewrite it. I'm going to go ahead. We're going to use our inverse tangent button. So I'm going to say inverse tangent is, or inverse, not is, but inverse tangent of the ratio of y over x, so root 6 over -2. And so I'll put this in on my calculator. Now you might remember earlier we mentioned this, they said they want to give the answer in degrees. And so if your calculator is in radians, go ahead and switch it into degrees. And in doing so, I'm getting an answer of about negative 50.8 degrees. And oops. So negative 50.8 degrees. However, we have a small problem. And that problem is that this angle is down here in the fourth quadrant, but we can see clearly from our picture that our angle should be in the second quadrant. And so that's not a problem that we don't know how to fix. Again, the reason that is because inverse tangent is always going to give you an answer in the first or fourth quadrant because of the range of the inverse tangent function. And so we can outsmart our calculator. Anytime that happens, we're just going to add a half a revolution or 180 degrees. And so if we do that, that will give me the correct angle that we want. So in doing so, I got 129.3 degrees approximately. And so then now we have R and we also have our angle. So my final answer will be Z equals R, which is root 10. Cis, I'll use the cis notation again, 129.3 degrees. Again, I would prefer that you just leave R as root 10. If we have the opportunity to give an exact answer, we like to do that. I guess that opportunity is not readily available when we're giving the angle. And so it's okay to round there, but I would just as well leave it as root 10 for your R value. And there you have it. So for our next two examples, we're just going to go the opposite direction. So right now we have complex numbers in polar form, and we're just going to change them to rectangular form. I think you'll find going this direction to be a little bit easier. Really, it's just a matter of simplifying. So finding the value of cosine 120 and the value of sine 120, and then we can simplify, distribute the two. And so we'll start with that. So cosine 120, so just use your knowledge of the unit circle to help you find that. So hopefully that's something you're still familiar with. So cosine 120 is 30 degrees past 90, so cosine value will be negative over there. I believe that's going to be negative 1/2. And then plus I times the sine of 120, and sine is positive there, so we'll say root 3/2. And then we'll just simplify, we'll distribute the 2, so 2 times negative 1/2 will be negative 1, plus I root 3. The 2's cancel, so just 2 here, we're just distributing. And let's try that again, there we go. And then distribute here as well. And so the 2 here cancels with the 2 here, and so here's our answer in rectangular form. So this is our x value and our y value. So remember the x plus I y. And so x is -1, our y would be root 3. And doing that is as simple as that. We're done. Here's one other. So I have 2 times cosine of pi over 18. So pi over 18 is not something that I know off the top of my head from the unit circle. And so we'll use our calculators to help us out here. Since pi over 18 is in radians, we probably are going to need to change our calculators back to radians. And so I'm just going to type in cosine of pi over 18 after switching it to radians. And I got something like 0.9848, etc. So I'm just going to multiply that by 2. I'm going to go ahead and do that all in one step. And I guess I'll just have one answer here. And so that gives me about 1.9696. So I'm going to say 1.96. Actually, I'm going to go round up and say 1.970. So I'm going to round 3 places. So about 1.970 will be my x value or my real value. And then I'll do the same thing. I'm going to do sine pi over 18. And I'm going to multiply that by 2. I'm going to go ahead and distribute the 2, and I get about 0.348. Again, I think the book examples go 3 places, so I'll do the same, and then don't forget to attach your I. So this is your real number part, this is your imaginary part. And so that's all you got to do. So sometimes the sine and cosine values will be ones that you're familiar with. You won't need your calculator. If it's an angle that's not on a unit circle, then just grab your calculator and just make sure it's in radians or degrees as the angle is given to you. Okay, so the last part of today's lesson is we're going to find the product and the quotient of complex numbers. And so they give us a formula for that we can use. Actually, a pretty friendly formula. I think I'm going to show you where the formulas come from, of course, but you know, once you get familiar with the formula, I think you're going to find it to be relatively easy to use. And so the formula is, again, we're just using lowercase z to be our complex number in polar form. So we're multiplying z1 times z2. And the formula reads that it's r1 times r2 times the quantity, the cosine of the sum of the two angles plus I sine the sum of the two angles. And so we can still use our cis notation here. In fact, I will when I do my examples. So an easier way of writing this would be r1 times r2 times cis, the sum of angle 1 plus angle 2. So remember, cis just means cosine of some angle, and in this case we just have the sum of two angles plus I, the I goes with the I, the imaginary I, and then S is the sine of, in this case, the sum of two angles. I do want to briefly show you where this formula comes from. If you don't care, you can skip right over this, but here it is in case you wondered. And so first, this is just z1 times z2, so this is z1, this is z2. And so I think at first we just kind of rearrange. I brought the R2 out front, and then we're going to FOIL the two sums. And so when you do that, you get cosine theta 1 times cosine theta 2 plus I sine theta 2 cosine theta 1. That's this one in the back term. And then the inner terms, you get I sine theta 1 cosine theta 2. And then the last terms, you get I squared sine theta 1 theta 2. So then actually that should read, I left out a sign, there should be a sign right here. It looks like, let me fix that real quick. So sine theta 1 sine theta 2. Okay, so then just a little bit of regrouping and factoring. So if you put the real terms together as a group and then the imaginary terms together as a group and factor out the I. And then you might recognize this is identity 2. So remember that list of 27 identities that we studied back in chapter 7. This one, if you read it from right to left, cosine of an angle, cosine of another angle minus the sine of the first angle, sine of the second angle is the same as the cosine of a sum. So that was identity number 2. And this one here is identity number 7. And so by substituting those, you end up with R1, R2 times the quantity cosine, the sum of the angles plus I sine the sum of the angles. And that's your product formula. Okay, and then here's our quotient formula. I put it in both forms. Here's the expanded form, and here's your cis notation form. Again, I will probably use the cis notation form. So this time, instead of the product of R1 and R2, it's just the quotient. That makes sense since we're doing the quotient formula. And the only difference is instead of adding the two angles, we subtract the two angles. So very similar looking formula, just kind of the opposite of what we did for the product. So again, if you're interested, here is the proof as to why this works. This one starts off, again, you just take the one number and divide by the other, so z1 over z2, and you start by multiplying by the conjugate of the denominator. And so that would be cosine theta 2 minus I sine theta 2. So then you FOIL the bottom, FOIL the numerators, and you get this mess here. And then on the bottom, since it's a difference of squares, you get cosine squared theta 2 minus I squared sine squared theta 2. And then you might remember that I squared is the same as -1. So you end up, when you simplify this, you end up with just cosine squared theta 2 plus sine squared theta 2. So all that's just equal to 1. So this whole thing here is just equal to the number 1. And so that's why on this step, there's no more denominator. And so then I just regrouped and simplified the numerators and was left with this. And then again, we have 2 identities from chapter 7. So I think cosine of an angle, cosine of another angle, plus sine of an angle, sine of that second angle, that's identity 1. That's the cosine of a difference of 2 angles. And then this one here is identity 6. So factor the I out, and then you're left with identity 6. So sine of an angle, cosine of a second angle, minus cosine of the first angle, sine of the second. And that's the sine of a difference. So put that together, and you have what we know as our quotient formula. And again, I'm gonna tend to favor using the cis notation. It's a lot easier on the eyes to look at and a lot faster to write. All right, so let's look at these 2 formulas in action. This will be the last part of your assignment today. They're going to ask you to find the product and the quotient given to numbers in polar form. So let's start with the product. I think in the homework you're going to be asked to do both of these things. So let's start with the product. So we'll find ZW first. So again, we just multiply the 2 R values. So it'll be 2 times 4. And then cis, you have the sum of the angles. It's as simple as that. So 40 degrees plus 20 degrees. And so then we'll just simplify a little bit. So ZW equals 2 times 4, which is 8, cis 60 degrees. And we're done. That's it. That's your answer. And notice it says express your answer in polar form. You might be wondering, like, should I find the cosine of 60 and the sine of 60 and actually, you know, simplify that and substitute those values in? But it's not asking us to. It's asking us to leave your answer in polar form, which is actually a good thing. That's very friendly. We just leave it like this. We don't have to worry about the sine or cosine values of 60 or do any sort of substituting. So since it asks us to put it in polar form, we're done with the product. And then the quotient, we'll do the same thing. We'll just say Z over W equals 2 over 4. So this time we divide the 2 R values. And then we say times cis, the difference of the 2 angles. So this time we'll do, instead of 40 plus 20, we'll do 40 minus 20 degrees. And so I like to leave mine in fraction form. I suppose you could say 0.5, but I'm just going to leave mine in fraction form. I'm going to say 1/2 cis 20 degrees. And again, since the directions ask us or tell us to leave it in polar form, we'll just say this is our answer. This is polar form. No need to find the cosine or sine value of 20, and we're done. All right, let's do one more of those. We'll go a little bit quicker this time. So the product, ZW. So it'd be 3 times, if there's no number here, just assume there's a 1 there. And so we'll say 3 times 1. Cis. Now this time the angles are a little less friendly. They're in radian form. So they have pi's attached to them. So adding pi over 10 and pi over 8, I guess I want to do common denominators. So I think I'll use 40ths for that. So if I multiply the first one by 4, I'm going to get 4 pi over 40. And for the product, I just want to add the second one. If I multiply that by 5, I'll get 5 pi over 40. And so simplifying that gives me 3 times 1, which is 3. Cis, and I'll just add the numerators. So that's going to be 9 pi over 40. And that is our answer. All right, easy enough. And then for the quotient, last part here, we'll do 3 over 1, which will still give us 3. And this time we're going to subtract. So I'm going to go ahead and use the work that I already did up here. I'm going to use 4 pi over 40 and subtract 5 pi over 40. And 3 divided by 1 is still 3. So that's going to give me 3 cis. And then 4 minus 5 will be negative. I'm going to put parentheses here since I have a negative so it doesn't look like I'm subtracting. I'm going to say cis negative pi over 40. Now, an argument could be had, like, is this an okay answer? The book actually does not give any answers with negative angle values. So I don't think it would be wrong if I left it this way, but I'm going to go ahead and follow the book's lead. And so if I were looking at the angle negative pi over 40, it would look like this, right? And so I'm just going to give the positive version of that. So I want to give the angle between 0 and 2 pi. And I would encourage you to do the same. That's how I'm going to give my answers when you check those. And so we can get that very simply. Just add 1 revolution. So add 2 pi to that angle. And so that would be like 2 pi would be, if we're talking about 40ths, wouldn't that be 80 pi over 40? And so if I add 80 pi over 40 to negative 1 pi over 40, that is going to give me an answer of, a final answer of 3 cis. So negative 1 plus 80 will be 79 pi over 40. And so that would be the answer that I prefer that you give. And I think if you look at any of the examples in the book, you'll notice they kind of do the same thing. And so for all of your answers, don't give any negative angles. If that happens, just add a revolution to that, and you should have a positive angle that we can give instead. All right, again, the directions ask for polar form, so we've done what it asks, and no need to find the cosine or sine value of 79 pi over 4. So we can just leave our answer like this, and we're done. All right, if you haven't seen the homework yet, here it is. It's page 609. We're going to do 14 through 40 evens. I'll put all the answers in the section for today's work in the Google Classroom, so you can check those as you go or when you're done. And then I would encourage you to use that cis notation. That's how I expressed all my answers, and it's certainly faster and easier to write. And so I would encourage you to do the same thing. And so good luck with that. As always, if you have questions, please reach out to me via email, message, whatever works for you. Let me know how I can help. All right, good luck. We'll see you next time.